My name is John Gilnessy. I work in business development at DEP. I also work as a program manager with our ion sensor team and also for our COVID-19 products, which includes face shields, gowns, protective barriers, and non-invasive ventilator prototypes. DEP is doing our part during this COVID pandemic, and we hope you're all staying as safe as possible and practicing social distancing. So first, I'll provide a quick overview of Detroit Engineered Products. We're a 21-year-old company with about 450 employees in 6 global locations. We're headquartered in Troy, Michigan. We specialize in engineering services, advanced design and simulation, and reverse engineering. DEP is best known for our engine ion sensor and our Meshworks engineering software. Meshworks is an engineering software platform for morphing CAD and CAE data to new variants and also providing world-class meshing. DEP supports all major industries and takes on many co-development roles, including the ability to take full responsibility for product development, validation, testing, and prototype delivery. Our engineering team, in partnership with our Meshworks software, ensure our clients' products are best meet performance standards. We also support commercial projects, defense-related projects, and we partner with research universities and national labs. We can take full responsibility for product development and innovation from design to validation and prototype delivery. DEP has completed over 900 projects for our clients, and we're especially proud of our current endeavors. We have many innovative technologies to reduce product development cycles and better achieve results for performance criteria. So today we're going to concentrate on DEP's engine ion sensor. I'll give a quick overview, and then Kamal Assad will get into the ion sensor details. So what DEP has done is we've multi-purposed glow plugs, spark plugs, fuel injectors, and we can also provide standalone sensors to interpret the ion signal that occurs during combustion. We've been able to take a multitude of lab equipment and corroborate results so that we can achieve a number of performance factor understandings. And Kamal's going to get into those right now. Kamal?
Well, thank you so much, John. Let me share my screen, please. Well, hello everyone. I hope everyone can see the screen. This is Kamal Assad. I'm the lead technical project engineer at Detroit Engineered Products, responsible for combustion ionization sensors projects. Today I would like to give a quick introduction about what is combustion ionization and also what can combustion ionization help internal combustion engines achieve. Through some applications for spark plug, glow plug, or gasoline and diesel engines. So first I will go through a very brief introduction. As all may know that combustion engines are required to meet stringent emissions standards in order and also in addition to targets of fuel economy and performance to achieve goals of those performance and fuel economy and emissions. So hence there is a need for an in-cylinder combustion sensor that is a volume produced unit to give feedback to electronic control units of the engines. There have been many techniques that have been investigated, including crankshaft dynamics, optical sensors, in-cylinder pressure transducers, techniques that are based on neural analysis, but all of these techniques are very expensive and are limited to lab environment. Today I'm going to introduce also another technique called the combustion ionization sensing or ion current systems that are found to be very durable and also have a very low maintenance and initial cost. So basically, what is ionization? Ionization occurs when combustion happens only during combustion inside the combustion chamber. The energy released due to the chemical reactions as well as the high heat generated ionizes the reactant species, the air and fuel mixtures, and thus breaking the bonds with the electrons, producing loose negatively charged electrons and positive ions of reactant species. When a voltage potential is applied across an electrically insulated probe, in this case our sensors, within the combustion chamber and the engine block, electrons get attracted to the positively charged probe, while ions get attracted to the nearby engine ground. This movement of electrons and ion produces an electrical current. Had this current been flowing through a resistance with a known value, ionization current measurement would be possible, which provides more information about the combustion. So by dual purposing an existing part of the ignition system within the combustion chamber, ionization measurement would be possible without the need to drill another hole into the combustion chamber to accommodate any extra sensors. So by achieving this ionization measurement and then having ion sensors pick up the ion current signal and pass it to an ion processing unit. This ion processing unit is a volume production electronic module that captures and processes the ion current signal in real time. It also contains algorithms to calculate important combustion and emission parameters from the processed ion current signal. Also, it's capable to communicate those combustion and emission parameters such as start of combustion timing, CF50, burn duration, misfire count, NOx detection, peak pressure, and NOx and soot emissions per engine cycles on a cycle-by-cycle basis to send those to engine control units through various communication protocols such as CAN bus communication. This process would actually enable the engine control unit to take informed decisions for combustion feedback control to achieve better fuel economy, performance, and less emissions. Thus, our services here include the modification of a spark plug for gasoline engines, a glow plug for diesel engines, a standalone ion sensor, or a fuel injector for direct injection engines to add ionization measurement functionality to it. Plus also providing the ion processing unit in addition to its calibration on a specified engine family. Calibration of the IPU is typically a 3 to 4 weeks process that our engineering team goes to OEMs, test facilities equipped with the combustion and emission test benches to configure and install the ionization system, collect data, and calibrate the system against the test bench measurement devices. This calibration would be valid for all engines of the same type, unless major changes to combustion chamber geometry or intake manifold or turbocharger are introduced. So ionization is actually not a very new topic. It has been investigated years before. What would be different in our case? There has been investigation about conventional combustion ionization system that actually use the sparking core of a spark plug or the central electrode as an electrode to measure combustion ionization. But only this happens after igniting the charge. So first, an ignition command is provided to the ignition coil to start charging for the ignition.
Sorry, Kamal, to interrupt.
Followed by an actual arc generation at the end of the spark discharge event to ignite the air-fuel mixture and initiate the combustion process and flame propagation process. Then the circuit actually, there is a switching circuit that is switches between between ignition functionality and combustion ionization measurement functionality. All of this would actually produce a lot of electromagnetic field and of high frequency and voltage and cause interferences, EMI interferences, which distort the ion current signal. So previous techniques were not able to achieve a clear noise-free signals as we do. Also, ionization measurement was not feasible during the ignition process since the sparking electrode is connected to the ignition circuit only. But our designs and our patented designs.
Yeah, can you please try on the slideshow mode because the slides are not coming properly.
It,
You have to, go to the full screen mode in the display setting.
yep.
Yeah, now it's correct. Yeah, thank you. Sorry about that.
Yeah. Sorry about that. So in order to enable combustion ionization measurement simultaneously with igniting the air-fuel mixture charge, the patent design of the spark plug combustion ionization sensor encloses a dedicated EMI shielded ion current sensor away from any sparking core or any sparking noise that might affect the signal. So for example, here, as you can see, the design eliminates the need to use switching circuits to switch between ignition and ionization measurement functionalities. Also, with the ability to measure ion current signal for the whole engine cycle, more capabilities are added to the combustion sensing system, such as pre-ignition detection. When you compare the blue and red traces, as you can see on the screen here, of the ion current signal of a conventional spark plug versus the patented smart spark plug, you will find less noise from the ignition event affecting the signal. This design would actually provide a clear noise-free ion current signal, which is really representative of the combustion process. As you can see on the screen, there is no EMI affecting the combustion ionization signal. Also, what's unique about us is since the ion current is produced by the ionized species that depend mainly on the combustion parameters like temperature and pressure, physics-based algorithms that extract combustion information from the ionized species obtained by some characteristics of the ion current signal on a cycle-by-cycle basis are built and embedded within the ion processing unit. In this case, ion processing unit would process one signal from the glow plug or the spark plug and obtain more information about the combustion and emission just from one ion current signal. So with this having been said, ion sensors would develop to capture clear noise-free combustion ionization signal. This is what makes us different. Spark plug combustion ionization sensors are patented designs that would fit in a metric 14 or a metric 12 spark plugs. Glow plug ion current sensors also available for diesel engines with sizes ranging from metric 8 to metric 12. Next, I would like to go through some applications in the next slides to show the merits of using combustion ionization sensors for feedback control of the combustion process. Experiments were conducted within an in-house research and development projects as well as customer-funded projects. Starting with gasoline engine application, here you can see on the screen a 2011 Buick Regal with a 2-liter turbocharged EcoTech engine has been equipped with a smart combustion ionization sensing system. This ionization sensing system consists of the ion processing unit as the brain of the system that collects crankshaft position, camshaft position, manifold absolute pressure, ignition command, and smart spark plug ion sensor signal. At our testing facility located in Waterford, Michigan, the vehicle is actually coupled to eddy current axle hub dynos that would provide loading on the engine wheels to simulate different road load conditions. Combustion and emission test bench equipment has been also available to perform combustion and emission analysis, which would also be needed to calibrate the ionization sensing system. The testing equipment includes in-cylinder pressure transducer within the engine cylinder head, high-speed intake manifold absolute pressure sensor in the air intake manifold, combustion analyzer data acquisition system that's connected to the pressure transducer and the crankshaft position sensor to provide data on a cyclic basis, fuel flow meters and NOx sensors and other temperature sensors across the test cell. So the first application I would like to discuss here today would be misfire detection in gasoline engines. In order to test misfire and to show the ability to detect misfire using the ionization system, a simple manual switch relay circuit is installed to interrupt the ignition command provided from the ECU to the ignition coil. This would actually interrupt also the combustion process itself, only in one cylinder of the 4 cylinders of the engine. Cycle-by-cycle traces shown on the graph here would show actually combustion pressure in yellow, injection command in orange, ignition command in light blue, and ion current signal in red. So during combustion, you would actually see ion current signal. But when the switch to induce the misfire is pressed, the ignition command is interrupted in order to disable the spark plug ignition. When combustion is interrupted, also ion current signal goes to 0, indicating that misfire is detected within those cycles. When the switch is switched back to its normal position, ignition command is no longer interrupted, and both pressure transducer and ion current sensor show signals representative of the combustion process. Also, you can see on the screen a chart that shows peak pressure reported by the pressure transducer in blue and misfire detection by the ion processing unit in gray. Those show that when combustion is interrupted, peak pressure reported decreases to the engine motoring pressure, and at the same time, IPU raises a flag to report misfire. This would actually provide a very cost-effective solution to detect misfire directly inside the combustion chamber instead of the indirect techniques of misfire detection by interpretations of crankshaft position sensors and cylinder firing order. Next application will be the measurement of combustion and emission parameters from the ion current system after completing the calibration process of the sensing system. So basically, the same vehicle that when coupled on the dyno unit, the vehicle was driven in a speed control mode at different speeds ranging from 2,000 RPM to 5,000 RPM, and with an increment of 500 RPM at each step. This is represented here in the blue graph. And at each speed condition, accelerator pedal position was pressed up to 90% of its maximum position to load the engine while holding the speed constant, as represented by the green trace that is indicative mean effective pressure in bars, which is a measure of engine load. This is also measured from the pressure transducer. Next, we're going to show a comparison of the indicative mean effective pressure reported by the very expensive lab equipment represented in the blue trace, in this case the pressure transducer, versus the same reported by the ion processing unit at different engine speed and different engine loads. Also, if a regression correlation is built between the two, the linear regression coefficient in this case reaches about 98% of accuracy. This is just to show you how accurate were the data reported by the IPU for this run. Another comparison would be, or another parameter that was investigated, is peak pressure. A comparison of peak pressure measured by the pressure transducer in blue trace is compared to the peak pressure per cycle calculated by the ionization system. Again, in this case, the linear regression coefficient reaches about 94.5% to show you how accurate is the measurement of peak pressure from ionization signal. Similarly, there would be other combustion and emission parameters that could be investigated per customer's request, such as CA50 of the combustion, burn duration, engine output NOx, and fuel flow. All of these parameters could be also investigated and calculated from the ion processing system. Another application that I would like to discuss briefly here is the knock detection capability. Knock actually occurs when air-fuel mixture charge is being compressed by the flame front during the flame propagation process. When the compressed charge reaches auto-ignition temperatures, knock occurs that could actually cause engine damage if not mitigated. The graph here shows the ignition command signal in red being advanced to induce engine knock, pressure transducer signal in green, which is affected by high frequency waves due to engine knock also, and ion current signal in blue, which is also representative of knock, which has the same behavior when knock is induced. In this case, knock frequency could be obtained using frequency analysis of the ion current signal to extract the high frequency component due to particular cylinder knock. This method helps to widen the knock limits of the engine map, as more accurate knock information could be obtained cylinder to cylinder basis instead of mounting just a knock sensor to the whole engine block. In addition, individual cylinder control is made easier if an ion sensor is installed in each cylinder of the engine, thus advancing or retarding the ignition command for each specific cylinder would be possible without penalizing the whole cylinders in case of one cylinder is knocking. Now, switching to some diesel engine applications, next I would like to show you neutral fuel engine operation using the ion current sensing system. For this experiment, a John Deere 4.5 liter diesel engine was tested using a glow plug ion current sensor, as you can see on the screen. To better understand this concept, this experiment is actually repeated twice. In the first try, combustion ionization was only monitored without using the feedback signal to control the engine. As you can see on the screen, pressure trace in red, ion signal is in black, and start of injection event is in green, while the engine is actually running on ultra-low sulfur diesel. On the fly, while the engine is running, an engineer is going to switch the fuel supply line to be connected to a different fuel. In this case, the fuel is going to be Sasol, which is a very low cetane fuel that requires a lot of time to combust, unlike diesel. As a result, ignition occurs much later in the cycle because it takes a lot of time for the fuel to heat up, mix with the air properly, and then auto-ignite. So without feedback, the ECU would still be injecting the fuel in the same crank angle degree, and as a result, late combustion is going to occur, and hence loss of engine performance, high fuel consumption, and high levels of emissions are presented. But doing a second run, ECU algorithm was actually modified to use information provided from the ion signal to adjust its injection timing to compensate for the different ignition delay periods of fuels. In this case, a closed-loop control has been built to demand the location of the start of ion signal to occur at a certain crank angle degree. When the fuel being injected is switched, ion current signals start to occur later in the cycle, but due to the feedback control signal, ECU starts advancing the injection timing in crank angle degree to compensate for the longer ignition delay of the Sasol fuel. Thus, engine performance, fuel economy, and emissions could be optimized by using the ion current signal to differentiate between the different types of fuels. The last application I would like to show you for compression ignition engines or diesel engines is peak pressure NOx and soot estimation. So typically we would work with OEMs to do the complete packaging study of design, development, and fabrication of the glow plug ion current sensors and specify their location within the combustion chamber. After that, to complete the calibration process, engine would be instrumented with combustion and emission test benches like the in-cylinder pressure transducer, NOx measurement, and opacity or soot measurement devices, along with the ionization measurement, glow plug sensors, and the ion processing units. As you can see on the bottom video, this shows you the test setup of the engine while running on a eddy current dyno with combustion and emission test benches connected to it. The IPU or the IC user interface was actually developed to visualize ion current signal processed by the IPU in real time and shows the combustion and emission parameters extracted from the ion current signal on a cycle-by-cycle basis, and those parameters are sent to the engine control unit through CAN bus or any different communication protocol. Similarly, a comparison of combustion and emission parameters measured by the lab test benches in blue traces are compared with the same calculated by the ionization system on a cycle-by-cycle basis for different engine speeds and load conditions. Quite good match for the data with linear regression coefficients about 84.5% for soot, 94% for peak pressure, and 91% for engine out NOx. So as a summary, the ionization technologies has a lot of potential for in-cylinder combustion sensing on a volume production level with capabilities ranging from combustion anomalies like misfire, pre-ignition, and knock detection, combustion and emission parameters such as peak pressure, NOx and soot estimations on a cycle basis. Also, cyclic variability is one parameter that could be investigated also. So with this, I would like to conclude the technical session of the combustion ionization technology.